Okay, so finding the limit of a function as x approaches c. Okay, so the limit of a function as x approaches c, c needs to be a constant, so limit as x approaches 2, limit as x approaches -1, something like that, exists if and only if the function is approaching the same value. Value of a function is the y value for the function at x equals c. So same elevation. So is approaching the same elevation from both the left and right sides of C. Okay, so we're going to start you with a graphical approach here. I've got a function, it's a parabola, y equals f of x. And so the limit as x approaches 0. So in other words, if I sneak up on the left and the right-hand side of x equals 0, what is the function approaching? Well, if I sneak up from the left-hand side, looks like it's approaching elevation -2. If I approach from the right-hand side, looks like approaching elevation -2. They're both approaching the same elevation. So the limit as x approaches 0 for f of x is -2. Okay, so how about the limit as x approaches 1? Well, if I sneak up on 1 from the left-hand side and the right-hand side, it looks like they're both approaching elevation -3. And so therefore the limit as x approaches 1 for f of x is -3. Okay. How about the limit as x approaches 2? So if I sneak up on 2 from the left-hand side and the right-hand side, it looks like they're both approaching elevation -1. Limit as x approaches 3. Well, if I sneak up from the left-hand side, looks like it's approaching elevation 3. If I sneak up on the right-hand side of it, it looks like it's approaching elevation 3. So the limit as x approaches 3 is 3. And let's try one last one here. So the limit as x approaches -1. So -1 from the left-hand side, from the right-hand side. Now it's not a whole number. Looks like it's about 1.5. So about 1.5. But all of those limits existed because from the left-hand side of the C and from the right-hand side of the C, they were both approaching the same y value. Okay, you go ahead and try problem number 2 here right now, and I'm going to go ahead and fill those in. Now, D, save D for us to do together, but do all the others very quickly. Okay, so just checking in with those very quickly. Limit as x approaches 0 is -3. Limit as x approaches 1. Now, just if you said does not exist, let's see what's going on. As I sneak up on 1 from the left-hand side, doesn't it seem to be approaching elevation -2? And if I sneak up on it from the right-hand side of x equals 1, doesn't it seem to be approaching elevation 2? -2, I mean. Now, you might say, but there's a hole there. That's okay. The limit can exist even if there's a hole there. Does the left-hand limit equal the right-hand limit? yes, they both agree that it's going to be elevation -2. Therefore, the overall limit as x approaches, the limit as x approaches 1, from the left is -2, from the right is -2, therefore the overall limit is -2. Okay, part C is 0, part E is 2, part F is -2, part G is, it's about 1/2, and H is 2. Okay, let's talk about part D, which is the limit as x approaches 3. Okay, so if I sneak up from the left-hand side of 3, and go towards 3, the left-hand limit appears to be 3. In fact, let's write that out here. So the limit as x approaches 3 from the left. Okay, how do I show that it's coming from the left? I put a little negative where it looks like the exponent should be for that. Okay, so limit as x approaches 3 from the left for g of x is 3. Now, if I go to the right-hand side of 3 and go towards 3 from the right-hand side, it appears that it's going towards 1. Let's write that out. Limit as x approaches 3 from the right. Well, if I want to come from the right, it's a little plus in the exponent spot there. Of g of x is 1. Now, remember the definition. For the limit to exist, you have to be sneaking up on the same elevation from both the left and the right-hand sides. So this one, we're not coming upon the same elevation from both sides. Therefore, the overall limit as x approaches 3 does not exist. Left-hand limit exists, the right-hand limit exists, but the overall limit does not exist. Okay, so tell you what, you do problem number 3 very quickly here. However, we're going to talk about B and I separately. Okay, so do all the others very quickly. Okay, so checking those answers, the limit as x approaches 0, it's about 0.5. Limit as x approaches 2, it's 3. Limit as x approaches 3, that's 2. Yes, I know there's a hole there, but we talked about that on the last one. The left-hand limit and the right-hand limit both agree at 2. And limit as x approaches 4, it's about 1.5. If you said like 1.6 or 1.7, okay, but limit as x approaches -4. It's about 0.5. You know, maybe you said 0.3 or 0.4. Okay. Limit as x approaches -3 is 0. Limit as x approaches -2 is -1. Okay, let's talk about these last two. So if I did the limit as x approaches 1, well, from the left-hand side of 1, so go to the left of 1, I would have to go down to intersect with the graph, and as I go towards 1, it's going down forever. Well, what y value is down forever? -infinity. Now, it's not an actual number, it's just indicating that it goes down forever. So the limit as x approaches 1 from the left for h of x is -infinity. If I sneak up on it from the right-hand side, so go to the right of x equals 1, and then I have to go up to intersect with the graph, and as I go towards as I go towards x equals 1, I'm going up forever, which, what's up forever? Positive infinity. So the limit as x approaches 1 from the right of h of x is positive infinity. Okay, now, if you have left-hand limit, right-hand limits that are infinities of some sort, the overall limit really does not exist. But particularly since one's negative infinity, one's positive infinity, the overall limit does not exist. So this one does not exist. And if we check out the limit as x approaches -1, well, from the left-hand side, it's going to negative infinity. From the right-hand side, it's going to positive infinity. So a very similar thing is happening here, and therefore the overall limit as x approaches -1 does not exist also. Okay, flip it over onto the backside. We're going to take a look at the backside. Okay, so now we just checked out the graphical, and if only we had nice graphs of every function out there on graph paper, and then limits would just be wonderful because it would be so easy. But we have to have a variety of methods here. We need to understand a variety of methods. Looking ahead to calculus, we need to always be trying to understand things graphically as well as numerically and analytically. So numerically, we need to go ahead and take a look at this. Scientific calculators needed. We're going to be plugging in some values. Okay, so for example, let's take a look at number 5 here. So if this is our function, if g of x equals x cubed plus 125 over x squared minus 2x minus 35, then we're trying to find the limit as x approaches -5. So we're getting closer and closer to -5 from the left and the right-hand side. We're going to plug in these values for x and evaluate them. Scientific calculators needed. As you're plugging in values like this, you really need to put parentheses around the numerator and parentheses around the denominator. Okay, so if we plug in those values, if I plug in a -6, I get -7. Now, I've worked these out ahead of time, so it's going to go a lot faster. It takes some time. You can help each other as you're plugging in these values. You might have to do a little bit of approximation, 2 or 3 decimal place approximation at least. Okay, so if I plug in -5.5, we get approximately -6.62. We plug in the -5.1, we get approximately -6.323. We plug in the -5.01, we get approximately -6.257. Okay, so now let's sneak up on it from the right-hand side. If we plug in a -4, we get approximately -5.455. If we plug in the -4.5, we get approximately -5.891. If we plug in the -4.9, we get approximately -6.177. And if we plug in the -4.99, we get approximately -6.242. So as we sneak up from -5 on the left-hand side and the right-hand side, let's look at the values. Are they approaching the same value? Well, these are doggone close, aren't they? In fact, it looks like if we plug in the -5, it looks like we should actually get about -6.25. And so since they're approaching the same value, therefore the overall limit does exist, and it looks like -6.25. Now, numerically can be a pain, particularly if you're having to generate these values. Thankfully, we don't have very many of these. You can help each other out as you're filling in tables of values. The other method that we have to be able to do is analytical. Okay, analytical indicates that there's a lot of algebra involved. Here are some methods that we have. If you can simply plug in the c without the denominator becoming 0, plug in the c. Factoring and reducing is used a lot. And sometimes it's necessary to multiply top and bottom by the conjugate and then plug in the value of c. Usually there's some factoring and reducing that happens after multiplying by the conjugate. And if none of these methods work, then probably the limit does not exist. Check this out. Number 7, limit as x approaches 2. So if I plug 2 into the denominator, I get 4 plus 16 plus 15. It's not 0, so I'm just going to plug in 2 wherever I see x's. So I get 4 plus 16 plus 15. Plug it into the numerator as well. So 4 plus 6 minus 10. And we get 0 over 35, which is 0. 0 in the numerator is not a problem. 0 over 35, that's just 0. So the limit as x approaches 0 for this function is 0. Okay, that happens. Limit as x approaches 3. Can I simply plug in 3 wherever I see the x's? Well, check the denominator. 3 squared plus 3, that's 12. Minus 12 is 0. I can't just plug in 3 for this function, at least not yet. So let's see if we can factor and reduce. Start with the denominator maybe. You can start either in the numerator or the denominator. So x plus 4, x minus 3. Well, yes, there's a factor that's becoming 0. That's what's causing the the denominator to become 0. Let's factor the numerator. And we see that there is a common factor of x minus 3. So if we reduce the common factor, we can now plug in 3 for the remaining x's, and I get 9 plus 2 over 3 plus 4, which is 11 sevenths. Okay, so the limit as x approaches 3 for this function is 11 sevenths. Let's try the next one. Limit as x approaches -2. Well, if I try just plugging the -2 into the denominator, I see that I get 0. -8 plus 8, that's 0. Now, usually if I do get 0 in the denominator, I will check the numerator also. I know I didn't check it on the last one, but let's check it on this one. So -2 if I square it is 4, minus 8 times -2, that's 16, so 4 plus 16 minus 20. So we get 0 over 0. Now, whenever you get the 0 over 0, the limit is almost always going to work out somehow. In fact, what's happening with when you have that 0 over 0 situation, typically what's happening is, remember on the front side when we were doing the graphical and we had the hole where the limit existed, the left-hand limit and the right-hand limit were both approaching the same value. It's that situation when you have the 0 over 0 happening. Okay, so we're going to try to factor and reduce. Now, until I actually plug in -2 for all the x's, I have to keep on writing limit as x approaches -2. So the x cubed plus 8, that's sum of cubes, so x plus 2 times x squared minus 2x plus 4. And the top factors is x minus 10 times x plus 2. And the x plus 2's are in common, and they were the part that was causing the denominator to become 0 and the numerator to become 0. And so, yes, there was a hole in the graph at x equals -2. But now that we've reduced out the part that was causing the problem, we now plug in -2 for the remaining x's. and I get negative 2 minus 10 over 4 plus 4 plus 4. So that is negative 12 over 12, which is negative 1. Okay, so there was a hole in the graph at x equals negative 2 because of that 0 over 0 thing. But the limit, the overall limit as x approaches negative 2 did exist. So it was one of those graphs where the overall limit did exist because it was the left-hand limit and the right-hand limit were approaching the same elevation, which is negative 1. Okay. Trying the next problem here. Can I simply plug in 49? No, I get 0 in the denominator. Check in the numerator, I would get 0 in the numerator as well. So this one should work out. Now, there's a couple different ways to do this one. I am going to choose to do this one by factoring root x minus 7 times root x plus 7. And so the root x minus 7s reduce, and that leaves us with 1 over root 49 plus 7, which is 1/14. Okay, let's try number 11. So if I just try plugging in a 2, I get 0 in the denominator, and the numerator, we do not get 0. So, in fact, we get 16 over 0. So if we're getting a 0 in the denominator but not a 0 in the numerator, this is one of those situations where the limit does not exist. Now, once we actually learn how to graph these functions, we can, which is this unit, but we don't know how to graph them yet, we will see that the limit does not exist as x approaches 2 for this one. Okay, finally, the very last problem that we have here, number 12, limit as x approaches 0. Can I simply plug in 0? No, the denominator is 0. Can I factor and reduce? Well, not in any way that we are used to factoring. Well, there's one method we haven't used yet, multiplying by the conjugate. So the conjugate, it might be the numerator or the denominator, but looking at this problem, it needs to be the numerator. So it's typically going to be the kind of the weirder looking one probably. So the top is the weirder looking one. So the conjugate, remember conjugate pair, a plus b, a minus b. So this is the a minus b. So we're going to multiply top and bottom by a plus b. And we have to multiply top and bottom by the same thing. That way we're actually multiplying by 1. We're not changing the value of the original problem. We're just changing what it looks like if we're multiplying by 1. Yes, I need to fill in the square roots. 49 plus 3x, 49 plus 3x. The only thing that's different from this conjugate pair to this one is that it's a 7 minus the root and then the 7 plus the root, but everything else is exactly the same. Okay, so limit as x approaches 0. Now, the conjugate pair, multiply them out. It's just a minus b times a plus b. So that's a squared minus b squared. So we get 49. The middle terms eliminate. And I'm left with the negative root times the positive root, which is negative, and square root times square root, the square root goes away. We get left with 49 plus 3x. Now, I will need to distribute the negative. Now, the denominator, if they're not conjugates, leave them in factored form. So x times the conjugate, 7 plus root 49 plus 3x. I want that x to reduce out. Okay, now if I distribute the negative up here on the top and combine like terms, 49 minus 3x, distributing the negative, I get negative 3x. And that's factored form, -3 times x. The bottom is factored form, x times the conjugate. So the x's are a common factor and reduce. And so if we take the limit as x approaches 0, I get -3 over 7 plus the square root of 49 plus 0, which is the square root of 49, which is 7. And so we're left with -3 over 14.